Dear colleagues, in the today lecture I'm going to go through the lexical analysis step of the compiler. What is the role of a lexical analyzer? Basic terms applied, speaking about a lexical analyzer, definition and identification of tokens, error handling and buffering. So, lexical analyzer is responsible for creating a series of the tokens from a series of characters, processing the source text. And it is typically not done in a single step. So typically not the whole source text is processed in a single run and passed to the syntax analysis as a series of tokens. But in contrast, typically the syntax analyzer asks the lexical analyzer to provide the next token and the next token and the next token when the syntax is checked and grammar rules specify potentials for additional tokens available at the input. Meanwhile, the symbol table is utilized as well. For example, if certain series of characters cannot be identified as predefined literals, they are considered to be identifiers and placed in the symbol table. And for example, the types of the identifiers are to be discovered by the syntax analysis. The lexical analyzer typically identifies tokens by patterns. So, token is a block in the source text, which is to be syntactically and semantically identified in a way, treated in a way, and represented by a single symbol in a grammar. However, there could be multiple patterns converted to the same token, like identifier may include several alphanumerical symbols, and any series of them can be considered as a pattern, which is identified as a token of representing an identifier in the source text. And its actual occurrence in the text is called lexeme. So for example, plus and minus operator can be placed in the same locations in the source text according to the grammar rules, and the same lexeme, the same token can be assigned to them. However, at certain point we are certainly interested in whether it was a plus or minus sign, and we have to refer to the lexeme, which clarifies the question whether it was a plus sign or a minus sign. During the exploration, additional information can be assigned to the tokens, like in the case of variables or any kind of identifiers. The the location of the symbol table, the description can be linked somehow to the token, for example, by a pointer to a record. And in some cases, for example, if we have an assignment operator, additional information is not stored. And in this case, at this point, the description remains empty. So, how tokens can be, the patterns of tokens can be given and identified. Typically, since we are at the very beginning of the process executed by a compiler, we are going to apply as simple tools as we can. And that's why the patterns are typically defined by regular expressions or regular definitions, and that's why they can be easily identified by a finite automata, which can be implemented easily, as you will see in the practical lesson next week. And as I mentioned previously, if none of these patterns matches a certain series of characters at the input, then it is assumed to be an identifier. Certainly the identifier can be expressed by regular expression as well. However, if it is very general, for example, like containing a letter at the beginning and any alphanumeric characters later on. In the case of the lexical analysis, error handling means manipulation of series of characters. What can we do with a character in order to correct an error? So if a certain pattern cannot be assigned to any of the types of the tokens, or the syntax analyzer reports that a certain location, that kind of token may not occur, then we try to modify the input to make it further processable. And the potential modifications include deletion of a character, insertion of a character, changing of a character, or swap to adjacent characters. And the basic principle is that we are looking for the series of modification that leads to a meaningful sequence with the least number of modifications. And in this case, this least number of sufficient modifications is called the number of errors. As I mentioned, identification of tokens is an iterative process performed by the lexical analyzer and typically initiated and directed by the syntax analyzer. And if the syntax analyzer contains a parsing procedure which is iterative or includes backtracks, then the syntax analyzer may ask for the same tokens again and again. The same situation may occur when the input contains some kind of typing errors, which has to be handled by the error handler. That's why the input is to be processed by the lexical analyzer multiple times, and that's why it works store the input or a certain part of it in an intermediate storage called buffer to avoid reading the source text from storage or from a communication channel again and again. The patterns, as I mentioned, are typically defined in a certain language, and as in the introduction, when we summarized the basic terms of the theory of the computation, you could remember that the alphabet is a finite series of symbols, the string is alphabet is a finite set of symbols, the string is a finite series of symbols, concatenation is a procedure how we construct a string by writing two strings one after the other. There is a so-called empty string which does not contain a symbol at all, and the language is a set of words or set of strings. And on languages as a set, we can apply operations like union. It is interpreted as a union of two sets of strings, and concatenation, which is similar to the Cartesian product of two sets, where the first half of the string is from one language and the other half is from the other language for each verse in the concatenated language. And clean closure is a language, results a language where we have such strings resulted by concatenation of a number of words from the original language. Okay, defining regular expressions less formally than in the theory of computations, mainly any symbol from the alphabet and also the empty string can be represented in a regular expression, and similarly the union is typically typed as this vertical bar, and the star represents the clean closure, and we can apply any number of parentheses. And the concatenation is simply written as two regular expressions one after the other. And you can see the language is represented by regular expressions. For example, for any symbol in the alphabet, the regular expression equal to the symbol represents a language containing a single word of the involving a single character written in the regular expression. And we can have longer strings resulted by concatenation or by clean star. In the case of computer programs, not only the clean star is applied for extending the length of symbols where 0 or more repetition is allowed, but also the question mark is applied, which means that a certain string represented by a regular expression is either written or either included in the language or not, or included in the string or not. And similarly, the plus sign means that the language involves any string represented by the regular expression, and also its extension by concatenating multiple copies of them. But in this case, the multiple means at least one, so we cannot result the empty string by the plus operator unless the original regular expression included the empty string or a question mark. And also in the practical implementation, we often use character classes where either the potential characters are listed in the square brackets, or a range of characters like A to Z is defined for those characters where their order is clear, which is typical for the letters in an alphabet and for numbers from 0 to 9. And besides regular expressions, we often apply regular definitions where we can assign IDs to a certain regular expression, and also there could be a series of some such assignments where the case identifier is defined by a regular expression on the basis of the elements of the alphabet and previous identifiers. So sequences, subsequences from regular expressions can be assigned to an identifier and repeated in a form where we do not have to rewrite the part of the regular expression, but instead we can write just the ID instead. And finally, how we are to construct a program code to identify certain tokens. First, if it is defined by a regular expression, we are going to construct a non-deterministic finite automaton by the Thompson's construction, where this non-deterministic finite automaton accepts exactly those strings which were defined by the regular expression. And then this non-deterministic finite automaton is to be converted to a deterministic one by the proof on the equivalence. And as a result, we have a deterministic finite automata, which is easy to implement since each step for each potential input symbol, we have a well-defined next state, and finally we do not have to do nothing else but check whether the actual state is included in the set of final states. And we are going to go through this process during the practical course next week. So we are going to specify certain types of tokens by regular expressions, then construct non-deterministic automaton accepting exactly these tokens, and then convert it to a deterministic finite automaton, and then implement the deterministic finite automaton in a programming language. Finally, able to check whether a series of symbols can match the definition of a token or not. So, as a summary, I can say that we went through the role of the lexical analyzer, the basic terms, and the definition of identification of tokens, error handling as this step, and the reason for buffering. Thank you for your attention.